assume that it's recording, and if it's not, then I'll re-record the presentation and upload it later for anyone that wants it, if anyone wants it. So again, I'm Derek Lura. I'm one of the faculty in the engineering department here at FGCU. Again, this presentation that I put together is kind of an overview of some technical notes that I thought would be useful for students who are working on their karts for this race and just kind of things generally. I don't know if I need to activate or if it's just like, there it goes. So just an overview of this presentation. I'm going to talk about some different technical aspects here, right? So kind of things with the roll bar, frame, and harness. Some concepts like rolling resistance, steering and differentials, power and batteries, and then kind of how you can look at motor curves and some rotational calculations. So I think for most of the teachers in the audience, this will probably be redundant with material you already know. But some of these things might be new to your students, and it might help facilitate discussions on different topics so they can look at these different technical aspects. So starting off, and you guys, this is just a video of a crash from a NASCAR qualifying event.
His second NASCAR Sprint Cup Series start. He finished 26th at Martinsville, but he made his NASCAR debut here in what was the Busch Series last November, started 17th, finished 20th. He was actually 29th quickest earlier, instead of 29:14. This car is locked into the show. It just walked up the hill big time. It bottomed out. That thing did a little turkey walk right up the track. Now, this car is locked in the show based on where David.
You guys know it's coming, right?
Prior to Rudeman getting out of this car, moving into the 40 Ford, replace the now retired Dale Jarrett in the UPS car. There was some talk of whether the team could switch points. Whoa, whoa, guys, whoa, whoa, oh no, oh my gosh! I have never seen anything like that in my life. He hit that wall a ton. Oh my gosh!
Not a whole lot of the car left, right?
Michael's moving around in the car. My goodness, that car just hooked, went straight in. It did that hook and go up the hill, man. And that was an incredibly hard impact.
You can see when they hit the wall. Important note.
Right there, how it just crushed all that stuff. That is good, though. That means that thing moved. It's great. It's just incredible how hard it hit. And then the flipping helped the car dissipate the remaining energy, parts flying off it. Look at that. Thank goodness. And wave to the fans. My goodness.
And he's okay, folks. Right?
For these race cars, it says so much.
So I think the impressiveness there is the severity of the crash and the fact he basically walks away from it, right? But what are the different aspects of that crash that resulted in him being able to walk away from that incident? What do you guys think? They go to the students that are in the room, or my students maybe?
Roll cage.
The roll cage, right? What else?
5-point harness.
5-point harness, what else?
Helmet.
What's that?
Helmet.
Helmet, right? What else? There's more things here. Those are the things that we can incorporate in our race, right? And those are definitely key things, but there's some more things here that does this.
Deflected wall.
The deflected ball, right? Did you guys see how much of the car was left after it was done rolling? Not that much, right? The portions of the car outside the roll cage are actually designed to basically slough off or to plastically deform to absorb energy during the crash, right? The wall is kind of the same thing. When you hit that wall, it's designed to deform, and that deformation uses energy and doesn't return it back to the car, and that helps, again, lower the amount of energy that gets absorbed by the driver. They also have something called a Hans device, which helps keep the neck in a certain position during the race, so that way you don't get whiplash, which is probably the #1 fatality and cause of injury in racing events prior to them using those devices, right? This is just going forward in the video, so I need to click on this presentation. So first and foremost, the roll cage and the frame, right? We have to keep the driver safe. We have to keep things outside, and the driver inside, right? So the roll cage helps to keep the outside out. The important things here, the roll cage really has to surround the driver, and it can't protect them if they don't stay inside it, right? It has to be structurally sound. If the roll cage fails, again, it's not going to help the driver, and it might even trap them inside the vehicle after the crash, right? And you have to have no hazards that can present a problem for other drivers. You don't want any members of your roll cage basically acting like a spear and lancing anyone next to you, right? So one of the things we look at here, if we're trying to see if the roll cage is sized appropriately, right, there should be a clear space between the driver and the roll cage regardless of which angle you look at the roll cage, right? So in this case, I have a front view and a side view. And from the front, this looks fine, right? Because the driver is totally surrounded by the cage. But then if I look at it from the side, I can see that his helmet is actually out past the edge of the cage. So that is not an acceptable design. It's not keeping the entirety of the driver inside the cage from any angle. And this is something that's pretty easy to check when you're inspecting your car. It's basically, if I look at the driver, regardless of where I'm standing, relative to the car, I can see that the roll cage is surrounding the driver. Now, the idea there is if you can look at it from all views and the roll cage is always around the driver, then you've basically created a capsule around the driver that will prevent them from being injured, right? Assuming they collide with something that is reasonably planar, right? Not something that's like going to glance into them, but there's always that issue, right? So that makes sense to everybody? All right. The strength of the roll cage is actually a much, much harder computation, right? So whether or not we know a roll cage is strong enough is a lot harder to justify whether or not it's the appropriate size, right? Determining the required strength of a frame is a really complex computation involving the total weight of the vehicle and the driver and the velocity that it's going to be traveling at. So if I have a frame that's safe at, say, 30 miles per hour, it's not going to be safe at 40 miles per hour because it only can support a certain amount of energy, right? So that impact energy is going to determine what is the safety rating on that frame. For the most part, you guys are not going to be able to do this calculation for your frame for all possible impact points. It's a very thorough and complex analysis. But a good rule of thumb is if you cannot support the entire weight of your cart and your driver on any point of the frame, then the frame is not sufficiently strong, right? So if you think about, if I'm going to change a member in my frame, take something out and put something on, if you would not be comfortable sitting in the cart, hanging the cart from that member of that frame, just that one point, then it's probably not strong enough. Does that make sense to you all? And again, this is a good kind of rule of thumb, because imagine if that cart were to roll or flip, right? It has to be able to support its entire weight at that point, otherwise that member could break during a crash. And so it's a good thing to just kind of think about if you're thinking about those different things, right? Most go-kart frames are safe to about 30 miles per hour, but if you start cutting things away from them, you're going to lower that safety rate, right? So think about that. You can also look at the specs for your individual frame. You get one that has a higher rating or a higher weight capacity or a higher speed capacity, right? Then that's going to be a safer frame generally, right? That's usually how they give you those specifications. If you guys want me to just go faster or slower on this, because I'm going into too much detail or not enough detail, just give me some feedback and we can go back and forth on that, right? Yes?
This is fine. This is my first year doing it, so don't feel bad.
Okay. The safety harness are really important because, again, they protect the driver. The most important part of the driver is generally their head. It's the most thing that's, you injure that, it's hardest to recover. The other thing you need to worry about is the neck, right? So in the NASCAR, they have this head and neck support, or the Hans device, which is really crucial in maintaining the safety of the part of your spine and your neck, right? A full helmet will also provide some of that protection. And this is why we want all our drivers to use a full helmet and not like a half helmet or a partial helmet, because that's going to help support the head and prevent them from being jostled around if they get into a crash, right? A 5-point harness is also very efficient at keeping the person in the seat. And if you look at the distribution of forces during a crash, if you have a 3-point harness, basically something that goes like this and this, there's less area over which the force can be distributed, right? And also you have less control over the appropriate positioning of those belts. So not as important for you to have a 5-point safety harness is have to be adjusted appropriately for both you and then attached appropriately to the frame of the vehicle, right? If it's not adjusted appropriately, then if it's tight, like on your crotch and loose on your waist, guess where all the weight is going to go when you crash? It's going to go to the tightest member first, right? So you got to make sure you have all those straps adjusted for each driver. And knowing how to quickly adjust those is going to be important for all of your drivers, especially in the relay, because you're going to want to get in and out of that quickly, right? Rolling resistance, I think, is probably the most important thing for this competition. If you lower your rolling resistance, you're going to do good in this race. And you have two primary means of losing energy in this kind of a race. You have wind resistance and rolling resistance, right? There's losses and gains from inertia in terms of accelerating and decelerating the car, but it's easier to control that just by not braking, right? As long as you're not braking, you're not losing energy due to inertia. So rolling resistance is pretty easy to calculate, right? If I know the weight of the vehicle and the driver, that's N, right? That's the total normal force or the weight of the vehicle and the driver, right? And then the coefficient of rolling resistance, CRR, right? That is a function of the materials and the pressure of the tires, right? It's usually easier to reduce the coefficient of the rolling resistance than it is to reduce the weight of the vehicle and the driver because we restrict the minimum weight of the vehicle, right? So really your design around here is going to be controlling rolling resistance. How many of you guys have looked at rolling resistance for your karts? A few of you? So it's going to be an important thing to look at. If you want to look at rolling resistance, what we really have in terms of rolling resistance is we have a primary point of contact, right? Due to the force deflection curve where the wheel hits the ground. So when we see this, the wheel, as far as the wheel goes, when it hits the ground, a portion of the wheel deflects, right? When it deflects, there's a certain profile between the force at that point, right, and the deflection of the wheel. And then when it comes back out, you get some of that force back, but there's always going to be some losses, right? So this is the force going in and the force coming out, and the difference between these two profiles is the energy lost per unit time. Right, because each point is basically going to go to the next point on the wheel, and the wheel is constantly rotating around. So one of the ways that we can control this is trying to decrease this deflection and to improve the elasticity of the tires, right? One of the things that you can do that's the easiest way to do this is just to get stiffer tires, right? Higher pressure tires, tires that have low viscosities, basically tires that aren't tacky or sticky, right? The more kind of rubbery your tires are, the more losses you're going to have associated with viscous forces, right? And the more losses you're going to have because you're going to have a total deformation that's larger. That deformation of the tire is larger, then there's more energy that's being put into each point, and so the proportion that you lose goes up, right? So for pneumatic tires, a higher pressure is generally going to be in a lower rolling resistance. The caveat to this is that you don't want to use tires past the rated pressure, not only because it's unsafe, because it might actually make your rolling resistance worse. And the reason for that is a lot of our tires have a cross-section that's reasonably square, like that, right? But if I overinflate my tire, I get a cross-section that looks kind of bulged out like that. And so now I'm deforming the tire by this bulb every time I go around, right? So you need to get tires that are actually rated for a higher pressure, and then you can decrease your rolling resistance. Sometimes you can increase or decrease it a little bit just by going on the higher range of your tire pressure. But once you start kind of overinflating that tire, then you lose the advantage, right? This is also something that's pretty easy to test, right? So if you want to measure the rolling resistance of your car, how many of you guys have a fish scale or a luggage scale somewhere in your shops or at home or something like that? None of you? Well, they're like $5 on Amazon, so you could buy one, and you can just pull your car. If I just pull my car with that fish scale, it'll tell you how much force it takes to roll that car at a low speed, right? And that's your rolling resistance. So that's really your rolling resistance in terms of force, right? And then you can make some change to the car, like I change out my tires or I change the pressure and then I do it again. If you lower that force it takes to pull the car, you've lowered your rolling resistance, and now you have a more efficient vehicle. Does that make sense? Also, a nice thing to like illustrate this concept, if you guys are looking at ways of kind of showing your students the difference, take a bicycle, inflate the tires to half pressure, do a couple laps around the parking lot, and then inflate the tires all the way to the full pressure, and then do it again. It is amazing the difference between having a low pressure or a high pressure tire. It illustrates the concept very, very easily, right? And you can feel the distance. As soon as you get on the bike, you say, oh man, this is hard. And you get on it again, you're like, oh man, this is easy, right? It's the same difference if you're looking at riding on like a BMX bike versus a road bike, right? Thin, narrow, very high pressure tires versus that squishy, low pressure tires. Any questions on any of that? No? You guys are all good? Right, the next thing, and this is a little bit harder to accomplish, has to do with the steering differentials, right? Not all wheels turn at the same rate when the car is turning, right? And this is because each of the wheels has a different distance to the center of the turning circle of the car, right? So the radius between this point down here, right, and this tire, and the distance between this point and this tire, and this point and this tire is all different, right? So that means that both the speed of the wheel, the rate at which it turns, right, and the angle of the wheel has to be different, right? The first part of this has to do with the Ackermann angle, right? And the Ackermann angle is basically a geometry that allows for the wheels to turn at different rates. So when I turn the steering wheel, the actual angle of the tires actually is not the same on both sides, right? You notice the inner tire actually turns a little bit more than the outer tire. Let me go back. So this one you can see it here. So you have more of an angle here and less of an angle out here. You can see that angle kind of changing more. With the inner angle, the inner tire has a larger angle than the outer tire, right? And the reason for that is, again, just look at this angle, right? This wheel is going to be all going around this central point. This wheel wants to go this way. This wheel wants to go this way. There's a difference between those two, right? And if you don't account for that, what's going to happen to the tires? They have to slip relative to the ground, right? So you're going to basically drag that tire across the arc, and you're going to lose a lot of energy basically rubbing against whatever the friction of your tire is. Okay? So you guys kind of, again, actually designing this into your steering geometry is a more complex exercise, but being aware of this will help you, look up what you need to find and put that in correctly, right? The other thing here, if you look at the differential of a car, right, even on the rear axle, since those two wheels are turning at different rates, right, the velocity of this outer wheel has to be more than the velocity of the inner wheel. So if I have both of those wheels turning at the same speed, basically I have a solid axle across the entire rear end, then one of those wheels has to slip to be able to turn, right? And again, if you imagine, I can stand in one point and then turn in a circle with a wheel on the end of a stick, and the wheel spins, right? But my point relative to the ground doesn't really change. So it's fairly easy to illustrate, and the more you're turning, the more losses you're going to have associated with that. That's going to help you improve your efficiency as well. And then the last thing, not the last thing I want to talk about, one of the last things that's probably more complicated has to do with your battery capacity. I think this is one of the more things you want to learn about in terms of not ruining your batteries, right? This shows the charge and discharge curve for a typical lead-acid battery, right? And then this is just an example, so it's not one that you should use, but you can find an equivalent curve probably for most of your commercial batteries, right? And this shows in red, we have a battery being charged, right? And this line here is the voltage being applied, this dark red line, to the battery, right? And then this dotted, that dashed line here, this is the actual voltage, or the internal voltage of the battery as it's charging, right? There's always a difference between the applied voltage and the internal voltage because there's some resistance there. And you'll note that this is fairly linear across the range until we get up past a certain point and it starts going up very, very quickly, right? And that's when we've reached the maximum capacity of that battery. And kind of the same thing down here. It decreases kind of linearly until you get about this range, and then it starts going down very quickly as you're discharging, right? So this is one of the things you can use, and if you calibrate this, you can know how charged your battery is based off its voltage, right? And you can also kind of check and see, am I overcharging or undercharging my battery based off that change in current or the change in voltage as a function of time, right? If you're looking at doing multiple batteries, which probably most of you are, just remember that voltage adds in series. So if I have two 12-volt batteries and I go from negative to positive, positive to negative, negative to positive, right? I'm putting them in series. So I'm putting the positive terminal, the negative terminal of the next one, right? Then I'm going to add those voltages together, so I get 24 volts, right? And the same amount of current has to go through both of those batteries. And that's important to remember because, again, if these things are charging or discharging at different rates, if the same current is going through them, then one of them may have a different voltage than the other, right? So this one may actually have 10 volts and that one might have 14 volts, right? Now I still get 24 volts, but I'm going to pull the same current for both of them. So if one of them is charged unevenly, then you could be pulling a lot of current from a battery that's already almost dead, right? And that'll break the battery essentially, right? Which can cause all kinds of bad things. Either just destroying the life of the battery or cause it to leak or overheat, things like that, show all that, right? If we add them in parallel, we have the same voltage across them, but we get more current, right? So that whatever current comes out of one battery, if I get the same current out of both of them, then we get twice the current coming out of this. So I can get more current at the same voltage, I can get more voltage at the same current. The total power coming out of the battery is basically the same either way, right? And it's always a good idea if you're putting batteries in series or parallel, make sure they're the same type, grade, everything like that of batteries. If you're mixing and matching different battery types, then that can lead to different kinds of issues as well. The charge controllers are really going to help you manage the batteries, right? They'll control the flow and the voltage and try and keep the charge managed so you don't undercharge your batteries or overcharge them. And they'll also control so that the batteries are producing power during the most optimal times, the optimal cycles. So they'll actually control the current, turning current or voltage on and off to allow it to deliver the voltage at a nominal value, right? For your motors, it's important to understand the efficiency curve for your motor, and this is a reasonably complex exercise, right? But understanding the motor curves allows you to pick an appropriate gear ratio. It allows you to select the appropriate voltage for the motor you're trying to use, right? And it allows you to maximize the efficiency at a desired speed, right? So this is a motor curve for, I think it's the Maxon, something like that, or Emax motor. I don't remember exactly which one this is. But it's the 0909 motor. And here you can see there's a lot of things going on in this chart, so which makes them kind of hard to read. But if we decompose this, it's actually not too bad, because really what it is it's 5 different charts superimposed on top of each other, right? So on this chart we have efficiency, watts, volts, amps, and RPM. And the way they generate these charts is I supply a known voltage to the motor. In this case, we're looking at, I think, 36 volts. Yeah, so this is a 36 volt test. You notice this 36 volts stays constant the entire time. And then what I do is I'm going to apply a torque to this motor, right? So starting at no torque, and I'm going to slowly increase the torque, and I'm going to measure everything else, right? So I'm controlling voltage and I'm controlling torque at the motor output. Everything else is just a resultant of those 2 parameters, right? So here we can see the voltage, and we see that it doesn't change over time. It stays at 36, and again, if it didn't stay at 36, then something's probably wrong with my test equipment, because I'm trying to supply 36 volts throughout this entire test, right? That may vary a little bit if you're doing a test yourself, because you may have a voltage source that can't actually produce 36 volts of power at whatever current this motor is trying to draw. And as you know, as we go further down the thing, it does go up to 200 amps, which is quite a bit of current, so you need a pretty powerful power supply to be able to run this kind of test, right? Probably one of the most important things we'll look at here is efficiency. And you may note here that the efficiency starts off low and then goes up very, very rapidly. What is the low end of this efficiency curve? What would that be? We're talking about zero torque. What is zero torque on a motor?
Neutral, no acceleration.
Well, so it's not necessarily no acceleration, right? Because if I'm running it inside the car, right, the car is always going to have some resistance, right? But if I were to decouple the motor entirely from the drive system, right, and then hit go, that would be the efficiency, right? Or if my motor is basically spinning up or spinning down without any force applied to it, basically I'm freewheeling, right? This is the very low efficiency. So it doesn't make really any efficiency unless it has to provide a force, right? But as soon as the force starts to come up, we see a spike in efficiency, right? So the efficiency goes up until I get to about 20 inch-pounds. This is pounds per inch, right? And then after I get to about 20 inch-pounds, then it comes down very slowly. So what does that tell me in terms of the torque of the motor? I can produce a fairly wide range of torques on this motor and still get a reasonably high efficiency, right? Now this motor doesn't go further down, but if I were to continue this chart out, what I would see is that at some point the motor would stall and the efficiency would again drop back down to 0, right? But on this one we get all the way up to 140 inch-pounds of torque, and that's for the test stops. So we don't know what the efficiency is going to be at any torque above that value, right? We can assume that it's going to be worse because we can see that it is going down as we get past that point, which is maybe why they didn't run the test further than that. They're like, it's efficient up to that point, we'll just let the consumer extrapolate based off of those results. The next thing we'll look at, and this is really important in determining how much fast you want to go, is the RPM, right? So how fast is the motor spinning at these different speeds? You'll notice that even at 0 torque, this motor is spinning at around 3,500 RPM, right? And it doesn't go down that quickly, right? where the torque is going up fairly quickly, the RPM does not change that fast, right? It's staying pretty level. And one of the things that this tells us is that as long as our speed is around that value, we should be able to balance out the speed of the motor, right, and the torque. So we can control the speed of the vehicle based off of the voltage that we apply to the motor, because the ideal speed, or the speed that it wants to run at, right, is going to be largely a function of the voltage applied across the terminals of the motors, right? And we also want to look at the amperage, because we want to know how much current is this thing going to draw out, right? And this is really important for our electrical system, because we have to know how much current we have to be able to supply if we want to get a certain amount of torque out of this system. And in this case, if we want to get the maximum torque out of this engine, so it's rated here at 104 pound-inches of torque, right? To get that much torque out, we need to supply 160 amps of current, which is quite a bit of current, right? And so if I don't want to blow out my electrical system, right, either I have to have a controller that can take that much current and fuses that can take that much current, or I have to have some kind of limiter where I'm not producing more torque than that based off the system, right? And again, your controllers can do that for you with different kind of pulse controls and things like that. The last thing here is the only kind of math I have on this, but it's important to be able to calculate the motor speed. If we have the velocity of the car, we can look at the angular velocity of the wheel. In this case, I have to know this with W. 2 pi, which is just in radians per one rotation of the wheel. That gets us the circumference of the wheel, right? And then I'm going to convert from minutes or RPM into seconds. So I want to get distance per unit second to get the velocity, right? So if I have an 8-inch wheel, which is a 0.2 millimeter radius, right, and I want to travel at 20 miles per hour, then I would say, okay, I have 20 miles per hour in meters per second is 9.8 meters per second. I can solve this equation for omega, right? And then I can get a angular velocity of 445 RPMs at my wheel, right? So if I want my wheel to have an angular velocity of 445 RPM, which gives me a linear velocity of the car of my 20 miles per hour, and there's some rounding error there, but about 20 miles per hour, right? Then I need to have a gear ratio such that if my motor is going to travel at 3,000 RPM from the chart that we have here, right, then I need a gear ratio of 6.7. So every time the motor turns over, right, it's only going to turn the wheel 6.7 of a turn, right? Or the motor turns 6.7 times for every time the wheel turns over. That make sense? And again, I can change that gear ratio to change the desired velocity of the car and try and tune my efficiency to get close to that peak efficiency of the curve, right? And then that'll help you save your batteries and make them last. I hope that was useful for some of you. And again, I can send this presentation out to everyone in the group if you want it. And I hope to be able to give you guys more resources as I kind of learn what it is you are interested in having support. And that's one of the things that the liaisons can help with as well. If you want more information on a technical basis, right, you can go to them and ask them. And if they don't know, then they can come to me and I can prepare materials to give to them or to give to you to help your students, better design or better evaluate their cars and come up with better designs and do, better during the race, right? Trying to raise the bar. Any questions? Yeah.
Is this presentation available online?
It's not yet, but I will send it out to everyone who's registered yet. Have you guys have any feedback on that yet?
So like for example, the safety check where we look at the roll cage. That's something. So what do you guys check the night before the race? What do you need all the drivers present, see to make sure I don't fit in the cart?
So
more obvious things like the electricity wire and all that stuff.
Yeah, so we look at the frame, and if you're using a pre-built frame and you haven't done any significant modifications to it, then usually we're just fine with that, right? If you're doing some modifications to the frame, then we'll look at a more careful evaluation of what have you changed and what are you using in terms of structural members, and what have you changed in terms of geometry. Have you made it too small or something like that? And then that can be an issue. So the word of advice there is don't modify your frames unless you really need to. For the most part, you're not going to see a significant decrease in weight by modifying the frame, and you're probably going to introduce some structural instability, right? Now, if you're building a frame entirely from scratch, it's a different issue, and we can work with you on, how we're going to verify and test to make sure that that frame is structurally capable, right? This is a more rigorous process then.
Is that all you guys inspect, or what else are you looking at?
So we have a full checklist of things that we check the day of the race in the rule book. So the inspection form is at the bottom of the rule book, and I'm not sure if this is 2018, so this should be the current rule book. And it hasn't changed drastically from the previous one, but this is the things that we check during the inspections, both the day of the race, and you guys should inspect to make sure you have all these things before you come out too, right? So check to make sure you have a full face helmet with DOT approved, right? You have the appropriate safety gear, your driver is the appropriate age for the race, right? We'll inspect the 5-point safety harness, the braking system, the roll cage, the panels, the quick disconnects to search the wiring for all of the systems, right? And this is really just kind of a basic check to make sure that everything is safe, right? The biggest thing that I have seen personally, at least from last year, was people doing things in the wiring where the wiring was not properly secured. So if your connections are not physical, actually connected, or at least well tightened, right? If I have loose wires that aren't actually touching each other, that becomes a very high resistance point, and that can cause fires. And fires during a car race is bad. Because there's one thing that's going to burn really good in that car, and it's all of your clothes, right? And probably the insulation on some of the wires. Like, you don't want to be on fire during a race. It's usually bad. It's also really bad for your efficiency because all that heat you're losing is energy you could send to your motor, right? So, yeah.
Are you going to do pre-inspections at our site?
We can do that. I know some of you guys wanted to do that last year, and that's something that we can coordinate either through the liaisons, or if you want us to come out or me to come out, then we can set up times for that as well. Yeah.
Wasn't there a day in March we can come over as well?
We are planning on having another event to kind of have you guys come onto campus at FGCU and have everyone get a chance to kind of network with the other teams prior to the event we don't have a date for that, but sometime in March. Yeah. And so if you guys wanted to bring your cards or come to ask questions during that, that'd be a good time to get feedback on, hey, I'm doing this or that, or this is our design, or what we're changing here.
If you don't know it, this rule book is posted on the Whitaker website. Cliff, you might not have seen that on
I've
there.
read through. I haven't gotten to I didn't see the last page.
Yeah.
Okay, I was gonna say I'll put a note here to send it to you.
I didn't know this was in there.
We just hit it so you can find it.
Yeah. I'll do
Yeah.
that for you.
It's supposed to be convenient because you just go to the end of the document and there it is. It was not intended to be.
Sorry, I'm asking all
Yeah, go ahead.
this is all stuff I need to know. So on Saturday, there's 2 races. It's a time trial, and then there's the relay race, right?
So both of the races are timed because it's a staggered start. The first race is 2 laps around the main loop at FGCU with the same driver. The second race is 4 laps with the driver changing at each lap, right? So the first race is a little bit more of a sprint in terms of you just go around as fast as you can. The second one is a little bit longer, it's a little more of an endurance race, and it has got the changeover element to it, right? Also, just kind of a general note, the battery capacity that we have in the cars now, you could run that whole race on just battery reserve, right? But augmenting the batteries and recharging between the races is one of the things that you can use to actually get more power out. So you're not just getting the power produced by the panels during the race, but you have the power produced by the panels between the races, right? So it's really kind of getting that recharge throughout the entire duration of the series of races, not just when you're actually driving the car, right? So the idea is you kind of want to start with a full battery and then charge the entire race, but still end with a almost empty battery. Probably not quite empty, because if you stop somewhere short of the finish line, then that's not going to work out for you. Any other questions or comments? Well, thanks for coming out, everybody. Christian, you're going to do tours of the ETI again if people want?
If anybody's interested, I know there were some students that wanted to see the facility. I'll show them around.
And then did all the liaisons get a chance to meet and talk with the teams that they're going to be working with?
Fort Myers isn't here, so.
So what we'll do is we'll reach out to them via email and see. Yeah.
That's it.
Yeah.
My team isn't here, right?
Your scene isn't here either, Caesar? Does everyone who is here that wants a liaison get a chance to talk with some of the students? Is anyone here who wanted a liaison that didn't have one assigned?
Well, we have one assigned. I don't know if she's here,
Natalia Nunez? She's right there.
Natalia.
She had to work, so that's why she came late. Anyone else? Just to be sure, yeah.
I just need to make sure I get it.
Okay. What team are you with? Naples High? Okay. I have a student for you.
Now, so my other question is, I saw she's one of our graduates.
Yeah.
So are you doing one per team, or?
And if Natalia wants to work with two of the teams, we can, or she can
That's not a
be.
big deal. Obviously, I don't want to take their personal lead.
She can be a lead, or what she can be a tentative liaison for both teams, and then what I'll do is I'll find someone else to work with either of you guys, if that's okay.
Well, she ain't carrying our secrets.
Yeah.
So then this is our first year having two teams, so I'm assuming that both teams need to have a presentation, so they count as two separate
They
teams.
count as two separate teams. Yeah.
And then for like the helmets, like we're probably gonna have, so for the endurance race, you need 8 drivers. So for two, so just I'm saying for both, or
Yeah. So the two teams are usually distinct. So you want to have, you don't have to have 4 drivers per kart, but you need at least 2 drivers per kart because you can swap back and forth. Yeah. But I would recommend that you have 4 drivers per kart, just because usually you have that many people on the team, and you know the students want to be a driver in the race for the most part. Yes.
Could you please introduce Michael too?
Oh, yeah.
To make sure the student liaisons have this contact information. He's
So-
our graduate student research assistant.
Michael, do you want
He'll
to
be handling-
introduce yourself, or?
I'm Michael Petty, Director of Research Assistant here at ETA. I've been working with the FTCs on the solar go-kart for a while now.
He's a good technical resource. All the liaisons will be able to contact Dr. Lura, myself, or Michael. Then you have, if they have any questions they can't get answered.
And everyone knows Christian, right? Okay. He needs no introduction.
There's nothing that changed like over since last year, like the wire size, gauge, or anything.
No, wire size is staying the same. The one thing that we are considering doing is that we're going to try and, again, mostly for future races, we're going to try and lower the battery capacity allowed, increase the solar capacity allowed. Just because the solar panels, their average production for the same size panels has gone up over the past few years. So getting panels that are, I think, the 270 watts is getting harder. And while they're still cheap and kind of abundant now, at some point those might be so outdated that you'll only be able to find 300 watt panels or something like that are a convenient form factor, right? Or at least if you want to get new panels. And then the idea that we're switching from more battery capacity to more solar capacity because more of a solar race, less of a battery race. So we'll transition that slowly, trying to keep with the technology. Other questions, comments, concerns? All right. So now that I have everyone's contact information here. So what I'm going to do after this meeting is I'll send emails out to everyone I have contact for with the liaisons. I'll have to get with Laura because I think she moved some people around, and so I don't know what the new setup is. But then we'll go back and forth to make sure that you guys have a liaison. You've been in contact with them, and if you have any questions, we can start opening up that communication a little bit more easily.
What was the weight limit that we finally came to?
Let me look. That's batteries, electrical drivetrain.
I know we talked about it when we were last time.
I think we changed it slightly, so weight of 460 pounds without driver. And this is the most recent version of the rule set, which is, I think, up on the website as well. How many, do you guys want to have some form of contact or communication for you or for the students besides just email? Does email work good for everybody? All right. Well, then if you guys want to stick around and ask additional questions, talk to me or with your liaisons, then that would be great. If you want to go on a tour with Christian, I'm sure he'll be willing to facilitate that. If not, then thank you all for coming, and we'll see you sometime in March.
Where's the bathroom?
The bathrooms, there's one set you go down here on the left.
Those are working.
Well, they were. As of Friday last week, right?
So.
You get your